Hi, I'm Yoav Weiss. I'm super excited to be here in Tel Aviv, speaking for the first time in my old neighborhood. My mom is here in the crowd, so fair warning, she may rush the stage. Uh, she may rush the stage with a banana at some point. Be warned. Yes, I work for Akamai. I work on making the web faster. And my job as part of that is split into two parts. On the one hand, I work on our optimization features. And as part of that, I see a lot of improperly cached content that could have been significantly faster if the developers would have set the right headers at the right time. At the same time, I also work on browsers, so contributing code to Chromium and WebKit, mostly around resource loading and mainly on preload recently. And as part of that, I see a lot of developers using those technologies and getting confused by the different browser caches. So I wanted to talk a bit about caching and hopefully reduce the level of confusion and magic around this subject. And this is not working. It's oh, yeah, okay. So as part of that, we'll discuss why should we as front-end developers care about caching. What are the different browser and network caches that our requests hit on their way to the origin server? What is HTTP caching and HTTP caching semantics? And finally, some best practices. How can you apply that to your day-to-day job? But first, why should we care? You most probably heard the saying that there are two hard things in computer science. The first one, naming things, is pretty obvious because giving something a short yet meaningful name is a very hard cognitive exercise. But the other one, cache invalidation, is less obvious. If you never had to deal with caches, you may not grasp at first why is cache invalidation extremely hard. If we look up the word cache's origins, it's coming from the French verb cacher, or to hide, which means that it's basically a hiding place for computer programs where they can stash data and use it around until they need it at a later time. So why, for a program, is deciding whether or not to keep data around for later use? Why is invalidating that data so hard that it's right up there on the Computer Science Hall of Shame, right alongside this? Well, first, when you're making a decision of storing something in the cache, you have to guess whether the data is something that will be valuable for you in the future. And we can't just keep everything around because we live in a world of finite resources, and after a short while of your cache running, putting resources in also means throwing something out. In other words, eviction means that we have to be fairly certain that the resource we put in the cache is more valuable than the one we're throwing out as a result. Second, when we're serving data from the cache, we have to be sure that it's still valid info and not some stale yesterday's news, in some cases literally. We have to be sure we're serving fresh content, which means that more often than not, we'll prefer to play it safe and revalidate the data even when that's not necessary. And looking at these 2 points together, you realize that cache invalidation is hard because it requires us to predict the future. Only time will tell if we made the right decision. The resource we just evicted to put in a new and shiny one instead, it may be needed a second from now, while the one we stored in cache instead is something we'll never see again. And that article you revalidated, most of the time you'll find that the resource did not change, so you paid an extra latency cost for revalidation. Your users paid an extra latency cost for revalidation for no good reason. But you can't know that ahead of time because we can't predict the future. But despite the fact that caching is hard, despite the fact that you can't always get it right, we have caches in computers all the way down to the CPU. CPUs have built-in caches, multiple layers of them. Each layer has a larger cache and is less expensive, but also slower to access. And when the CPU fails to find data in those caches, it look for it in RAM. And our operating systems keep RAM-based caches of popular disk areas to avoid fetching them again and again from disk. And many programs keep around data in RAM in order to avoid fetching it from disk, which is slow, or from the network, which is even slower and unpredictable. And just a few figures to get the orders of magnitude that we're talking about. An L1 cache hit from the CPU is half a nanosecond, which is fairly fast. Getting that same data from RAM is 200 times slower. Moving to the disk is 1,500 times slower than RAM. And the network is, on average, 1,000 times slower than disk. So if we look at the aggregate, it means that fetching something from the network versus the CPU cache can be 300 million times slower. And this is why we bother with caches. Yes, they're not perfect, they require complex logic, but the alternative is so much worse. The alternative can be 300 million times slower. And as performance-conscious front-end developers, latency is our nemesis, our arch enemy. And caching is its strongest, like its biggest weakness. So we've established that caching is awesome, but how does caching on the web look like? What are the different caches that a request hits on its way to your server? Well, at first, a request object is created inside the rendering engine. Its sole purpose is to find a matching resource and bring it back to the rendering engine in order to render the page. And there are different types of requests, different types of resources, and they all can be different from one another, other than obviously having a different URL to them. And the created request is looking for a resource, and the first place to look for that is in the closest cache, the memory cache. By the way, these are all drawings by my kid, who's awesome. So. So the memory cache, or as it should be called, the short-term memory cache, is part of the renderer and keeps in RAM resources that the renderer have seen before, but disappears as soon as the renderer is destroyed because the user clicked away. So if the resources we're looking for were previously loaded on that page or previous page, so either by the preloader, which is the browser's speculative parser, or by explicit preload link, or by multiple tags that all refer to the same resource, the resource would be in the memory cache, and our request can just use that and stop its quest to find a resource. The memory cache has a lot of different rules regarding which request it can match with which responses. URL matching is obviously a prerequisite, but also they have to match by type and by credential mode, as well as other different. It's a fairly complex set of conditions. At the same time, HTTP caching semantics are not necessarily a strict part of that, and at least for some request types, the memory cache will happily serve non-cacheable resources. And the assumption there is because the memory cache is volatile, there is no problem in terms of serving stale content. And all that logic is under spec, and as the web community should totally do a better job and specify that logic, probably as part of the fetch spec. But if a request didn't find the resource in the memory cache, it continues on and gets registered as an outgoing network request, both for resource timing as well as part of the DevTools timeline, which means that if a request was served from memory cache, you will not see it as part of your DevTools network tab or as part of resource timing. And after that registration, the request continues on to the service worker. And service workers, as I'm sure you've heard, are an extremely powerful in the browser JavaScript proxy, which enables you to manipulate requests and responses. And as such, they have their own cache API, which is explicit. And from the request perspective, they're totally unpredictable and can return anything as a response. And as such, they are not bound to HTTP semantics. The service worker can return a made-up response or a response to a different request or a response to a previous request of the same type that it's seen before. But if the service worker doesn't have a matching logic for a request, then it uses a fetch call to send the request further down to the network stack, which is often in a different process, which adds some extra latency. And at the net stack, we find ourselves at the HTTP cache, which is a rather strict cache and follows HTTP caching semantics to the letter, and we'll soon discuss what that means exactly. It does, for example, allow mixed type matches, unlike the memory cache, as well as, and its logic is well-defined as part of the HTTP RFC. It's also a persistent cache storage, which means that it has to evict resources, and it also means that it's 1,500 times slower than the memory cache, as we've seen before, even without taking the IPC boundaries of moving to the network stack into account. So if the HTTP cache has our response, that's great, but if not, we continue down in the network stack, and when we're using HTTP2, there's one more cache that our request has to check before it hits the network. And that's the H2 push cache, or as I like to call it, the unclaimed push stream container, which is much catchier as a name. H2 server push is a feature that enables the server to send down requests to the browser before the browser requested them. And when that happened, the requests are stored in the push cache, waiting for matching requests to come along. And once a request has matched the resource, it gets taken out of the push cache and often then goes into the HTTP cache. And the push cache is a non-persistent container that is owned by the H2 connection. So basically, that means that if the H2 connection is closed, the pushed resources are gone. When an unspecified timeout has passed, 5 minutes in Chromium, that resource is gone. And generally, again, this cache is really under-specced, and we should do a better job of specifying it. In the meantime, implementations may vary. But once we didn't find our request in the push cache, we move on to the network. And the network can be an extremely unpredictable medium, where latencies vary based on the network type and queues filling up along the network. Packets could get lost due to queues that fill up and throw packets out, collisions at the radio layer, data corruptions, and more. It's a pretty scary place. And latencies vary based on the type of network that we're dealing with. So Wi-Fi networks usually have low latencies, but can have high packet losses in scenarios where there are many users on a single Wi-Fi network, for example, conferences. And cellular networks have had traditionally high latencies, but they have decreased over the generations. And fiber, despite its reliability, still has to send light from one end of the globe to another, so still the speed of light is an inherent lower bound of our latency. And if latency is such a dominant factor in our web apps performing well, what can we do about that? Well, that's where CDNs come in. And by sitting as close as possible to the user's ISP gateway, CDN edge servers cache the content and are likely to serve the content from their internal cache rather than send it all the way up to the origin. They often also terminate TLS connections, which also lowers the cost of TLS connection establishment by lowering its latency. So if we found a resource in the edge cache, that's great. But if not, the CDN edge server forwards the request to the origin. And at the origin, we're likely to hit another proxy, which is the origin's reverse proxy. And since those two proxies, the reverse proxy and the origin, sit very close to one another, or in some cases even on the same machine, the role of that proxy here is not to lower network latency, because that is very low, but the role here is to lower the latency it takes the origin server to create dynamic content. Because when the server is creating dynamic content, it has to talk to databases and potentially fetch resources from different places across its network, or even external APIs, which can take a while and also takes a lot of CPU. And so if we have the same request hitting the server multiple times in a row, we can use a single response to serve all of them. And the reverse proxy caches are bound to their own semantics, and it's not really well specified, depends on whatever the web developer that configured them wanted them to do. And if our response is not there, we move on to the origin, which, at least in theory, must have our resource or generate it dynamically, and otherwise declare failure by sending us a 400 or a 500 response. And once we get back that response, once we unite our request and resource, they can start their way back and leave cached copies in all the caches along the way. So we talked a lot about HTTP caching semantics, but what is that exactly? Well, the good folks that defined the HTTP protocol realized that caching is an important part of the web's use case, and it can accelerate it significantly. And therefore added a bunch of caching directives to the protocol, first to HTTP 1.0, and then those caching directives got revamped as part of the HTTP 1.1 protocol. And one thing that is important to realize about HTTP caching semantics is that the resource URL is the cache key. If a request for the same URL arrives twice, the first response could be cached and used to serve the second one, and consecutive ones after that. Another key concept that is important to understand is freshness, because the freshness of the resource determines how long you can use that resource in order to serve it to users without revalidating it. And if you remember the predicting the future part that I talked about earlier, determining the right freshness for a resource is more or less it. If you include a max age directive of 3,600 seconds, you're basically telling the browser and any other cache along the way that you guarantee that this resource will not change for the next hour. But after that, it might. That means that if you shipped a bug or a typo and immediately figured it out, fixed it, and deployed it to production, your users may continue to see that bug for the next hour unless they refresh their browser, which is not great. And once that freshness lifetime ran out, that doesn't necessarily mean that the resource has changed. It just means that a cache has to revalidate it. And revalidation happens with conditional requests that are using validators. Validators are HTTP response headers, such as last modified and etag, which tell the cache this resource was last modified at this particular date, or provide a signature of the resource, which enable the cache to revalidate the resource at a relatively low cost by sending out requests with an if non-match and if modified since headers. Basically asking the server, did this thing change? And the server can then reply with a nah, or in HTTP, a 304 not modified response. And if the resource has changed, the server can just reply with a 200 OK message with the response body, just like it would normally do. So validators give us a way to revalidate the response without downloading the payload if it hasn't changed, which is awesome, but revalidation still has a cost. It still takes us a full round trip time, or RTT, to get the response back and know that we can use the resource that we have in the cache. Another aspect of HTTP caching directives is scope and who can cache said resources. For example, some resources, it's perfectly fine to cache them in the browser for a particular user, but they're an awful privacy breach if cached on the network as publicly cached resource, because they can reveal private information, potentially embarrassing information, such that some users are Python users, for example. So we can control that scope by using cache control directives such as cache control private to tell the caches that this resource should not be cached on as a public resource, or cache control public, which means exactly the opposite. Cacheability directives tell the cache if and how a resource is cacheable. We talked earlier about the two hardest things in computer science. Now I'll tell you about the two biggest lies in computer science. So cache control must revalidate, may not revalidate. Must revalidate means that your content will not be revalidated as long as it is fresh, but cannot be served stale once the freshness has actually run out. So this is something you can use when the content you serve will be invalid after the freshness has run out. The other one, cache control no cache, which will cache your content. But it means that it won't be served without revalidation, which is what you would have thought must revalidate means. Sorry. Cache control no store actually does what it says and avoids storing that resource on disk and evicts it from memory as soon as possible. This is something you should use for privacy-sensitive information, such as banking details. And stale while revalidate is a relatively new caching concept, a relatively new caching directive that enables a cache to serve the content stale once while revalidating that request at the same time. So the first user will get a stale response, but following users will get a fresh response that the cache has fetched in the meantime. And cache control immutable is another new directive that enables you to tell the browser this resource will never change. If it will change, we will change its URL and all the references to it. So the browser never has to revalidate that resource. Okay. So we just went over a large amount of possible header values, but you're just trying to make your content properly cacheable, right? So what should you do? Well, stealing the advice of Jake Archibald here, there are two main common patterns that you can follow in order to avoid the predicting the future issues we talked about earlier. The first one is immutable content. So if you have static content that you can change all the references to, for example, your script resources or your CSS resources, which you can version or add a hash to their URL, you should probably serve them as immutable content, which means that you can use either very long in the future max age header as well as the immutable directive. The reason you need both is that not all browsers support the immutable directive. In particular, Chrome will use a very long max age value as a heuristic to behave as if the content was declared immutable and avoid revalidating it, but doesn't support an explicit immutable header. So you need to include both in order to get full browser support. The second pattern that you can use for non-static resources, for resources where you cannot change the URL for its references, is to always revalidate that resource. One way to do that is cache control, no cache. A better way to do that is to use a very short max age in the area of seconds and use the must revalidate directive. That enables your reverse proxy or the CDN's edge server to cache that resource for a very short period of time. So if you have 1,000 requests a second hitting your servers, the cache in the way can offload most of them and just send you a single revalidation request every 5 seconds in this case. And everything else, in a way, is a gamble. Everything else requires us to predict the future and may cause us to find ourselves in a situation where we found a bug but are failing to update our site or have synchronization issues between our HTML content and our CSS content. Unless there is an interesting pattern in the CDN world, which we like to call hold till told, where we use it for rarely changed content and declare it basically immutable at the edge or long-term cacheable at the edge, and then use explicit purge instructions so that the developer can notify us whenever that resource has actually changed. So the content is cacheable practically forever, but if we push the bug to production or a false statement or the wrong price, we can just get rid of that content at a click of a button or an API call away. And wouldn't it be cool if we could bring that same pattern to the browser? Well, at first, when we talked about H2 push, people talked about using H2 push in order to create that invalidation from the server pattern. But the problem there, because of the structure of the caches, because the H2 push cache is based lower in the network stack than the HTTP cache, it's fairly hard to do that. It's not currently supported in any browser. And therefore, it's not really a practical option, at least not today. Another option to follow that pattern in the browser is to use the iframe reload pattern, where a long-term cached resource is loaded by the dynamically generated iframe, which the iframe is then reloaded using the reload function, which caused the browser to revalidate that resource. So we can use that pattern in order to revalidate certain resources in basically for the next time the user will come to our site. But the problem with that pattern is that it requires us to build that resource loading pattern as part of our application logic, as part of the DOM. And nowadays, we have a significantly easier pattern to follow, which is service workers. And because service workers have their own cache API and their own logic implemented in JavaScript, but at the same time are separated from our application logic, it means that we can implement that hold till told pattern and have resources cached in the service worker cache for a long time while communicating purge instructions in whatever way we choose all the way down to the browser. And such purge instructions could be as simple as keeping around a text file with a list of purge URLs that the service worker periodically checks on your origin and evicts such resources from cache as necessary. So, sum it up. Caching is important, and caching can be a bit complex and can be a bit daunting, but you shouldn't let that discourage you. You shouldn't neglect caching because it can make a huge difference when it comes to your site's performance. There are a lot of browser internal caches. Not all of them are spec'd and they have their quirks, but if you are using H2 push, if you're using preload, if you're using prefetch, you should be aware that these caches exist and you should know what they do and how they behave, because it will help you understand why the browser is behaving like it does. There are two common HTTP caching patterns that you should bear in mind: immutable and always revalidate. And service workers can enable us new and exciting caching patterns such as hold till told in the browser and much more.